the biggest mistake people left that there. Now how many bonds do you have to the carbon? 5. That can't be right. Carbon only has 4 bonds. So, and then it was straightforward, 2 heptanone. I think this is the answer I saw on 1 or 2 of the quizzes because people were studying for the exam already. So, okay. That's what I said. People are mixing up the exams and they're just memorizing answers rather than figuring out the principle behind it, which is the way you really want to study. Here, we saw this question. What? Take-home quiz already? We saw it here, and I think it was on the quiz that I also gave you. In other words, this is Markovnikov's rule. We're adding to the double bond. That means there's no double bond left. You're adding, oh, one of the quizzes I gave HBr. Guess what? I saw HBr. I saw bromine in this exam. Notice I added HCl this time. So this is, you know, you're studying, but you gotta sort of think while you're doing the study. I started over there and ran out of space, so I wrote the name over here. And basically, the one that has more hydrogens gets a hydrogen, breaks the double bond, and the bromine goes here. And I talked about carbocations and things, and the fast reaction and the slow reaction. These are all the kinetics considerations you'll spend more time with in organic chemistry. So, this is the product here. Chlorine goes with this one, and the extra hydrogen goes over here where there already was a hydrogen. And so it's 1, 2, 3, 4, 5. 2 chloro, 2 methyl, pentane. On the other quiz, I think it was an ethyl group in there, and so it was 2 methyl instead of 2 ethyl. That was whatever the name was. People wrote methyl also. Okay.
Dr. Anner?
Yes.
Does the chloro have to be over the
Yes.
methyl? Is that
Not over it. It's the hydrogen goes to this one that already has hydrogens. That's because of the stability, as I said, of the carbocation. The more methyl groups on there, the more stable it is. So it's going to last longer, so the bromine can come in, or the chlorine in this case, can come in and add. That was why we did the mechanism. But as I said, all you have to remember is the ones with more hydrogen get the more positive part. That's the way I stated it. This is the more positive part. This is the more negative. So the one with fewer hydrogen gets the more negative part. So what you're doing is breaking this double bond and forming, you do things like this, 2 new bonds. 1 to hydrogen, 1 to bromine. And so it has to be, or chlorine. Notice I'm saying bromine too, because that was the other quiz. Okay. But I wrote it right on the quiz here. Okay, so it has to be 2 chloro, 2. Then one of my other popular, this is identifying functional groups, and one of my other popular quizzes had this thing. I'm going to get a better one. This looks like this one. It says secondary alcohol. That's the thing that oxidizes to give you a ketone. This one has 3 R groups on it, so it's a tertiary alcohol. What do you get when you oxidize this? Nothing, because the only way you can oxidize it is by breaking up the chain, and then you get a bunch of nonsense in your test tube or your reaction glass. Or brown, oily tar, as they call it. You do enough organic chemistry, you'll see that a lot in the lab. You're supposed to look for a nice white crystalline material, and you get something brown and gooey in the bottom of your flask. You say, darn, I wish that hadn't happened. I have to start over. I'll get a D, whichever. Okay, coming back to this then. This is the CO2H. Almost everybody recognized carboxylic acid. I don't think I saw any spelling errors. This one, double bond, It's alkene, don't say ethene or anything like that, because the functional group is alkene, because here you can have anything, I put hydrogens there, but it doesn't matter, so it's just alkene. This is the ether. These are, in other words, it says down here, it can be any alkyl fragments, it's just methyl, ethyl, anything else. That's the ether. And this one, on one of the quizzes I had, I think I called it electron, double bond over that. And that, of course, was the ketone, but on this quiz I put an extra hydrogen on there, so that makes the CHO, which is the aldehyde. So the two mistakes I saw, most common ones, were from a different version of the quiz, where it was a secondary alcohol and a ketone. As I said, people study, and now you just have to study appropriately, I guess. Okay. Same thing with the next one. One of the quizzes had acetine, I think, or actinium, I forget which one, AC, actinium. And I got a lot of people made the product actinium, and they did things with this to make it work out to be actinium. There it is. It's 89. Yeah, that's what they did. They shipped it around. But that was a different quiz. And the other thing I saw, people wanted to get this thing here, and they wrote, I won't put everything. That's gonna work, yeah. B plus 1. But notice capture means it's gonna be on the left. And when it says electron, it's a -1. That's a what type of substance when it's +1? Positron. Oh, well, I said positron emission, no doubt. In other words, all these questions keep going up and people keep picking up the wrong answers. The idea is you write down the way it's supposed to go and then work it out. Okay, most people got this one right because I didn't make any big changes there from the previous quiz. Right, people had some trouble for people that didn't remember alpha 4 and 2. Oh, one person made some sort of mistake like this. This wasn't a mistake, and that wasn't a mistake either because that's what it is. But then they changed this number because they read the +1 for that thing there, and that's just what? +1 charge. It doesn't mean you have so many particles in the nucleus. It just means you have you're missing an electron. 2 electrons. Okay. And the safest thing is just to write the alpha. Okay. Moving on. Most people are okay with this problem. Few people, their calculator failed them. They had something like this, and then they came up with some weird answer. And I didn't recognize the answer from any of the other quizzes, so I think the calculator just messed up. And let's see, this is the problem. What you're doing is adding the free energies. That's just to remind you that you can't really add intensive properties like cell potentials. What else is there to say about this? Oh, somebody read the wrong cell potential from one of these things. The only thing I can say for that is, when you're reading across, make sure you put your paper across it so you read, or when you're doing a multiple choice question, put some sort of paper across on your Scantron so you know which question you're working on, so you don't mark the wrong answers for the wrong question. Because those are things where people go wrong sometimes. Okay? Then we got to the half-life problem. Okay? On the other quiz, I gave you the half-life and asked you to calculate something. I gave you the percent that was left. You could calculate that here, okay? But what a couple of people tried to do was by proportions. Because in Chem 2, when we say we're doing half-lives, and we start out with 2,000 nuclides or 2,000 atoms, after one half you have a half-life, you have 1,000. After two half-lives, you have 500. And so they set up proportions like that. But you have to work through the log ratio of those proportions. Okay? And a few people tried to convert it to atoms, but notice if you convert grams to atoms, you'll have the same factor here and here. And so there's no reason to do that. I said as long as they're the same units, milligrams, activities, counts, what else did we say? Numbers of atoms, because we could do it with numbers of atoms. But it's no reason, it's not necessary because the same factors will be here and here and they'll cancel out. Avogadro's number and things like that. So what the biggest mistake people did is lambda. But I asked you to calculate the half-life, and you immediately put what? This is the formula for the half-life, right? In other words, you put half-life divided into log. The formula for half-life is and I put a minus sign. No, I guess I changed it around to flip this over. So if I asked you for this and you plug it in as though you had it, you can't possibly be right. So a lot of people did that, and then they took that number and went through a bunch of these same operations. But basically, you have to use this information, that gives you this side of the equation, and you know the time, so what you have to do is calculate for the rate constant of decay. Once you know that, then you can go over here and calculate the half-life. So in the other quiz, we had half-life, and you had to calculate the rate constant. Here we had and then calculate the ratio. What did you do? Maybe it's the same problem. I forget what the take-home problem was. Oh well, coming back to this thing, I also did it down here. That's the half-life. What did I do here? I want to demonstrate something. Oh, I wasn't demonstrating anything. I'm just dividing that out. Okay. That was for me grading, because I wanted to see the numbers. But most people did this, as long as you had that set up right and came up with the right answer, it was okay. A couple of people wrote this, and then said T1/2 equals. And even if you got the right number here, you would have gotten at most 1 point out of that. Because I would have seen numbers in here to see what you did. So if you got the right answer by writing that without putting numbers in, and a lot of papers it says numbers because you left out a number I needed to see. If I didn't see the number and you got the wrong answer, you got 0 points of partial credit. One of the reasons, of course, is on the data sheet I wrote all the equations. I'm not going to give you any points for copying my equations from here onto your problem thing. Oh, okay. So just writing the equation wasn't any good unless you put some numbers in. Then if you made a math mistake, you only lost a point or so. But if you made other mistakes, you lost more points. So that's what this was. These were just the numbers, so I can see whether anybody got things right. So that gave me lambda, whichever way you did it. If you just wrote this with all the numbers in, and you came up with this answer, which is what most people did, I didn't take any points off for that because you showed me the mathematical setup with the numbers, you showed me the correct answer. I assume you can do this mentally or in your calculator. So you didn't have to do that detail with it. Once you knew what the half-life, once you knew what the rate constant was, you plug it in here. Then the bonus question, which only a few people got right. Let's see if I can up with this together on my time. Was based on this one. And the same sort of thing happened. People tried to do it by proportions. Stay here. Let's see it more or less there. Here, I wanted the activity. It is the same problem we had previously. So we had to say, somewhere along here, activity is equal to lambda times n, and you had to find out what n is. That's where people got into trouble. Because it's the same problem as before, you have the same half-life you had previously, and this is the half-life you got in the first problem, so I converted it to seconds because I wanted disintegrations per second. And so the wavelength, not the wavelength, wrong course, the rate constant is ln2 over the time in seconds, so now it came out in reciprocal seconds. So this is your rate constant, that's this number. Then the next thing you needed to know was how many atoms you had. And this was the tricky part, which most people missed. Somebody asked me on one of the practice quizzes, it had, I forget what T1/2 was, it was like 40 minutes or something like that. And it said, after 40 minutes, that meant if you started with 10,000 atoms, or whatever it was, they said, why did you divide it by half? Because after one half-life, you have half the amount left. But here I didn't give you a whole half-life, so you had to calculate how much was left. So I gave you the time at 448 minutes. So you put in your rate constant times the time, and it's equal to ln n over 45, the starting amount. The sample started at 45. So when you did that, this is the mass of the sample after 448 minutes. 5 or 6 people recognize that, and the rest of the people, a couple of people divided this by 2, because that's the way it was on one of the practice quizzes, but that's because on that practice quiz I had given you, after one half-life, how much was, what was the activity. So this was worth a bonus 5 points. In other words, if it's a bonus, it takes a lot more work to solve it. So that's why it's at the end. Okay. So basically, this is how many milligrams a sample. Then you convert it, and some people had some strange numbers here. It says SM155. I don't think I've used SM on any of my quizzes. I just picked a random nuclide to toss in there. So I don't know what kind of number, what quiz they were looking at, but they had a strange number in there. So this is how many atoms. Okay, it's 8.4 something or other. And then you take the NGT, that's the activity. Here's your rate constants, reciprocal seconds. And here's the number of atoms that came out in atoms per second. A few strange mistakes. Somebody had some, because they put in 10 to the minus 23 of it, something like that. 10 to the minus 23. And I had it at the top of the page, it's 10 to the plus 23. People get so used to sticking minus signs in there. And what they did is they got like something like 10 to the minus 3 or 10 to the minus 4 atoms per second. What that means is it takes 1,000 seconds before one atom disintegrates. And that works out to be a half-life of about 1 billion years, 10 to the 9th years or something. And there are some things that are that long, and people, you know, you always say in last semester, the nucleus should be unstable because you're packing all those positive charges together in a very small volume and repelling them. And recently I read somewhere, one of the stable nuclides of potassium, they observed a radioactive decay. it broke down into something simpler, even though it was stable, because it's had such a fantastically long half-life, nobody'd seen it before. So there are things like that, and that's what this number would say. You had something with some fantastically long half-life, and for all we know, if we look at it long enough, maybe there won't be any stable atoms at all. Okay? Stability is just a matter of degrees, I guess. So, anyhow, that's some of the strange answers I saw there. I had a different strange answer on one of the other quizzes. I'll get to that in a minute. Because this question was on the quiz 12 too, I think. Like I said, all these quizzes look the same to me. All I do is change some numbers here and there. See if people are awake. Any questions about that? Now, he's not going to have anything that detailed on the ACS exam. And I've done all I want to do with radiochemistry, but he's going to ask you something about half-lives. But it's not going to be that detailed calculation. And the reason I can't say exactly is because I have several different years of ACS exams, and they ask different questions each year. Okay. So let's go back and continue with the quiz. By the way, if you have questions, ask now, because this is your review. This is the end of this is the last time I'm going to lecture. Wednesday, we're done. You don't have to listen to me anymore. Unless you want to come back next year and do it. Some of you may. I don't know. Okay. Darn. What a nasty thing to say. Okay. Benzoic acid, I didn't care if you wrote it like this or you wrote CO2H, same thing. But again, and we talked about this, some people didn't put this in and they did that. What does that make it? I don't know, I can't name it. It's it's based on cyclohexane, and this must be, I don't know, maybe we'll call it cyclohexyl something. I can't think of any name for that. Anyhow, since I couldn't think of a name for it, it's wrong. Yes?
Confused for the... Oh, no, no, you didn't go for that.
Benzoic acid.
Okay.
A few people, most people got it right. A couple of people put too many extra bonds in there. That was the only thing. And a few people put a methyl group here. And down below they didn't. On the quiz that I gave, on the quiz 12, we had phenol. So most people recognize this thing, but again, there's some double bonds and too many bonds in here. And the big mistake here, on one of the past quizzes, I said 2,5-dinitrophenol instead of diamine, aminophenol. So a lot of people gave me the dinitro compound. They gave me the right place positions and everything, but they gave me the wrong substituent. That's what I said. I don't have to make much of a change, and it makes it easy when you have a word processor. It's a lot faster to write quizzes. And you just have to be thinking, which is the whole purpose of all this exercise. Then here's toluene. A lot of people had that right. Cyclohexanone. I don't know if it was the same people. I don't keep that kind of statistics in my mind. But a lot of people forgot to put in all the bonds for the saturated molecule. And so they left off some of these extra bonds, and I said show all bonds with a dash if necessary. A few people mixed up cis and trans, and a few people did things like this. And that now has 5 bonds to each of those carbons, which can't be right. What was the other question?
For D, puberty yet? Or
2,3-dichlorocyclohexanone.
But do those represent hydrogens or
Yes.
carbon?
Well, I said I'm using the old-fashioned way.
But then why would you?
How would you if you do this, so you're thinking of this, how do you do that when you're doing cyclohexanone? Or any cyclic saturated molecule?
Because I don't know for when you do it like that, because the same reason, because you don't show the hydrogens, for example, on...
Benzene, you never did. You used to do this, nowadays they do this.
What? I mean, there's still hydrogens coming off of those, right? Just
Yeah.
So then why would you show the hydrogens there but not there?
Because this is the way, if you did this, like I did, without the extra ones, I'll accept that.
So, but I also want to know why is it wrong for D? That's what I'm confused by. Like, you did.
Well, this is saturated, you need 4 bonds for each carbon.
But I always thought it was assumed that if there wasn't a bond there, that was a hydrogen. Just like it was for like...
But that means you only have how many hydrogens on this? 1, 2, 3, 4, 5, 6. And there's, carbon always wants 4 bonds. And I know what you're saying about this, and I do not know what the modern way of representing cyclohexanone is.
So that was just like, yeah, for example, when you have like a straight chain, it's the same thing. You don't
Yeah,
have to show
here you don't have to show the hydrogens. And I accepted that. Or, let's see, somebody gave me, no, nobody did it on that one. But, well, on the quiz, on the take-homes, a lot of people gave me those zigzag structures. That's fine, if you did it right, I accepted that. But I said, I don't know how you do this in that modern computerized notation, and I suspect you still have to do this sort of thing. Because I haven't looked at an organic book since they introduced that way of doing it. So in lecture, anyhow, in lecture, let's go back to what I said. If it's saturated, you have to show it. So that's what I'm going by, what I said. And that's the way the book does it too. Because your book's old-fashioned. He does have some of those zigzag structures in it. But the new modern organic books have more of them. And one of these years, maybe they do this, I don't know, I remember. Chair form and everything. But I think they still have to show, I don't know if they show the bonds or not. But I'm not worried about that. I think they have to show the bonds, because they talk about eclipsed and staggered and all that. So, whatever that means. So anyhow, in lecture when I did that as an example, I said, make sure you show me the saturated. And I said, for the benzene, the molecular structure's okay. People do, by the way, in the old days, not so much nowadays, do put the extra bond in you. That was just an accident when I was drawing the hexagons like that, right? But they do this sort of thing. So you see that some places, mostly in Chem 2 books. Okay, then the next one. Almost everybody got this right. I didn't mark it wrong, but a lot of people left off the capital M for molar. I'm trying to think, I can't think of any real mistakes in here. I think most people got this one right. So, are there any questions about that? If I marked something wrong, clarification of what I did? No. As I say, when I'm marking the same thing wrong on more than 2 or 3 papers, then I sort of remember it. But if I haven't marked anything really wrong more than one time on any question, I don't remember that kind of mistake because everybody's thinking about the right thing. This one, sometimes you can do it just by looking at the periodic table, but the only way you could combine these was to take these 2 equations like that, and this is the cell potential, which is positive, therefore yes.